picture the scene. It's 1999 and the long-awaited arrival of the Mars Climate Orbiter is about to land on the surface of Mars. It's been travelling for 10 months, but as soon as you get close to the surface, something is apparently wrong. It gets too close, it's going faster and faster, it doesn't slow down, doesn't launch its parachutes, and smashes into the surface of the planet, meaning that all of the data it could have collected is lost. Now, what caused it? Well, it's not due to a lack of funding. It was £150 million, a lot for 1999, and it had been travelling for 10 months without an issue. Now, what had happened was to do with units, and that is what today's video is about, the importance of using correct units. Now, imperial units such as pounds, feet, and inches are not good ones to use when we're talking about international collaboration in science, and this is what happened with the rocket. Scientists from America were using these units instead of the European scientists who were collaborating use meters and seconds, which aren't compatible units. So in the question of why are units important, well, if you use the wrong unit, so you have different teams collaborating using different units, you're going to run into problems. So we're going to look at SI units today, which are units that are used across the world by scientists and in particular physicists to make the world go round. So what are units for? Well, all quantities in science and in particular physics have a unit. That means something that comes after the number. Now, when we say quantities, what we mean is essentially anything, any product, property that can be measured or calculated. Okay, so we can look at some examples of each today. If you measure it or calculate it, we call it a quantity in physics. So there's a lot you would have come across from GCSE. I'm going to write out a list of some of the more memorable ones you might have seen before. So we've got meters, we've got amps, ohms, we've got meters per second, kilograms per meter cubed, newtons, joules, and you can see the rest of the list forming here. Now I want you to have a think as I'm finishing writing this list, how many of these can you measure directly? Could you measure meters directly with a piece of equipment? Could you measure joules directly? Could you measure degrees? Could you measure coulombs? And how many of these might be calculated units? Now, the ones we're going to measure, ones we're focused here, are degrees with a thermometer, meters with a ruler, amps with an ammeter, kilograms with a scale or balance, seconds with a stop clock, and we're also going to look at moles as well. Now, these units we call the SI base units. Okay, so SI, if you don't know, stands for it's a French word, stands for Système International or International System, and just means like the standard unit. Now, all these units are standard units. They're used instead of feet or pounds or square inches or something like that, but there are a particular set of units called SI base units. Now these are the ones I've circled here, and means that every single other unit on that list can be derived from those 6 base units. That's why they're really important, sometimes considered fundamental. So I'm just going to make a note of them up here on the side. There's one other one we're missing as well, so along with those 6 you also have the candela, which you won't really do anything with at A level, to be honest. It's to do with light intensity as well. So let's have a look then at how we can go about deriving these other units from those 6. So meters, kilograms, seconds, amperes or amps, degrees in Kelvin, not Celsius, moles as a unit of measurement. So as a quick note, if you're just starting A levels, we are going to use index form of units. So instead of m/s, we do m times by s to the power minus 1. It means the same thing. For example, 1 over x is the same as x to the power minus 1. So let's have a look at a couple from the list you might be surprised weren't on our fundamental base units list. The Newton is a good example. So how we express that is with an equation. Newton is force equals m times a, m is mass, kilograms, acceleration is meters per second squared, so we can express it like that. Joules we can express using force times work done. Now we know what force is already because I've just written it down, kilograms meters squared to the power minus 2, but with distance is in meters. Now how can I simplify this? I've got meters times meters, so now I've got meters squared, so that's the SI base unit for a joule. Next one we're going to look at is capital C, stands for Coulomb. I'm going to write that one in because it's a bit less common unit. So let's think of an equation we can use to help define it. I can use Q equals I times T. I is current, that's measured in amperes or amps. T is time, that's measured in seconds. So this one's quite a nice one actually. We can express coulombs as amps seconds. Next one let's have a look at is the watt. So watt is the unit of power. Now watt is equal to work done divided by time. Now work done is measured in joules. So I've already got that from the previous question, so I'm just copying that in. It's divided by time, so I divide by seconds. Now instead of writing it like this, I'm going to write s to the power minus 1 because it's easy to figure out how to simplify it. Because if I've got s to the power minus 2 times by s to the power minus 1, I add the indices, which means I get s to the power minus 3. Next one we're going to look at is another electrical one. We can look at the volt. Let's look at an equation we can use to calculate it. There are a couple. We'll do this one first. So it's energy or work done divided by charge. Energy is in joules, so let's copy the joules notation in there. Divide by charge. Now we just said charge is in amp seconds, so therefore those both go on the bottom, so I can write them a to the minus 1, s to the minus 1, and simplify the seconds down to s to the power minus 3. Now there's another couple of ways you can work out potential difference or voltage. I could use power divided by current. Now if you use our formula from power earlier and then just divide by current, you'll see they are exactly the same units, which is perfect. That's what should happen. Physics all links together, so it kind of works out. Now try a couple yourself. See if you can pause the video. I'm going to give you two. I'm going to give you ohms, and then I'm going to give you Teslas. So ohms, we can use resistance equals PD divided by current. So I'm going to put my value for PD in and divide by current, which means a to the power minus 2. So that's quite a nice one once we worked out the volt. Now Tesla only comes up once in GCSE. It comes up more at A level, but you can use the F equals BIL equation and rearrange it for B, for magnetic flux density. And we know what force is because we've written it down already. That's kilogram meters per second squared. Divide by current and divide by length. And because I've got M to the power 1 and m to the power minus 1, that cancels, so it looks a bit neater. We've got kilograms seconds to the minus 2, amps to the minus 1. Now, how would this come up in exam questions? It can be multiple choice, it can be like a show question. I'm going to go through one question with you, which is like a kind of show that units are consistent. So the ones they're going to look at is a show that the units for kinetic energy and work done are the same. Now I'm going to say base units just to make sure we're using those base units. Now kinetic energy, we should know the equation is half mv squared. The half doesn't have a unit. Mass is in kilograms, meters per second is squared. So if I simplify that out, I've got these units here. Kilograms meters squared per second squared. If I do work done, I've got force, which is mass times acceleration, times by distance, which is meters. So therefore, those units are perfectly compatible with each other, and we've proved that the units for energy in kinetic and work done are the same.